Welcome to The Explainer. Let's get right into it today, because we're exploring a truly massive technological shift. We're moving from the old era of frustrating terrestrial dead zones and randomly dropped calls to the absolute ultimate frontier of global connectivity. We are going off-planet. And the sheer amount of capital currently moving into the space sector to make this happen is just staggering.
So, you might be wondering, where exactly is the ultimate edge of this massive AI and data boom heading? Well, to find the answer, you really just need to look up. It isn't just happening in massive terrestrial data centers on the ground anymore. Those facilities are getting increasingly bottlenecked by earthbound fiber constraints and overwhelmed power grids. To solve this, the new edge is being pushed hundreds of miles above us, right into orbit.
We're literally witnessing a physical infrastructure overhaul on a scale we've never seen before. The massive global data supercycle, which is being fueled by hundreds of billions in capital expenditure from the world's largest tech companies, demands relentless, ubiquitous connectivity. We're now treating space as a direct, physical extension of our earthbound data superhighways. The stakes, and honestly, the financial gravity of this space tech supercycle have absolutely never been higher.
Here is our flight path for today. First, the orbital infrastructure boom, followed by Starlink's unbreakable connectivity, SpaceMobile's cellular orbit, Rocket Lab's launch capabilities, and finally, the gritty financial realities of the sector. Let's go!
Section 1. The orbital infrastructure boom. This is the foundational layer of the new space economy. Okay, so the crucial starting point here is understanding low Earth orbit, or LEO, which means altitudes of 2,000 kilometers or less. Now, why does this physical distance actually matter so much? It's simple physics. Light and radio waves take time to travel. By dropping from legacy geostationary orbits that sit way out at 35,000 kilometers down to just 500 or so, LEO networks slash latency to mere milliseconds. That makes them fully capable of handling intense AI edge computing, highly secure data transfers, and seamless everyday connectivity without that frustrating lag we're all used to.
Section 2. Starlink Connectivity, the unbreakable global link.
Look, we all know the misery of traditional in-flight Wi-Fi, right? Bouncing signals off geostationary satellites thousands of miles away results in brutal latency, constant dead zones over oceans, and those annoying captive portals demanding your credit card. While Starlink completely replaces that outdated paradigm with a zero-friction, gate-to-gate broadband experience that essentially mimics your home fiber network. There are no paywalls blocking basic connectivity, no complicated logins, it's just seamless, continuous internet access at 35,000 feet.
We are talking about a massive, game-changing technical leap here, blistering speeds that often exceed 200 megabits per second, with just 25 to 60 milliseconds of ping. To actually pull this off, phased array antennas on the aircraft are electronically steering beams, rapidly tracking and switching between hundreds of LEO satellites that are zipping by at 17,000 miles per hour right above them. For the very first time, passengers on partner airlines can stream 4K video, hold real-time Zoom calls, and work entirely in the cloud while mid-flight with zero buffering.
And just to show you how reliable this network has become, we have this pretty amazing confirmation. In response to a post showing him and NVIDIA CEO Jensen Huang aboard the presidential jet, Elon Musk simply replied, "Yep," confirming that Starlink is currently live on Air Force One. Think about that for a second. The presidential aircraft demands mission-critical, absolutely unbreakable communications for national security. Starlink is providing a global network with zero dead zones, ensuring uninterrupted command and control anywhere on Earth.
Section 3. SpaceMobile, bringing cellular to orbit.
Now the next frontier is direct-to-device cellular. SpaceMobile is attempting something that is incredibly difficult. They're building a space-based broadband network that talks directly to the standard, completely unmodified smartphone that's already in your pocket. No specialized satellite dishes on your roof or bulky external antennas required. This technology aims to instantly bridge the global digital divide, connecting nearly 6 billion existing mobile subscribers around the world just by having them look up at the sky.
But to capture a weak, standard cell phone signal from space requires some unbelievable physical scale. 2,400 square feet. That is the size of the phased arrays on AST's Next-Gen BlueBird satellites. They're essentially unfolding the largest commercial phased arrays ever deployed in orbit to act as massive floating cell towers in the vacuum of space. Just the engineering complexity of launching something all folded up and then reliably expanding it to the size of a tennis court in zero gravity is totally mind-bending.
Drilling down into the actual processing power required to run a giant antenna like that, we find AST's proprietary AST5000 application-specific integrated circuit, or ASIC. This custom piece of silicon acts as the brain managing thousands of connections simultaneously, which enables peak speeds of 120 megabits per second per coverage cell. And their earlier Block 1 testing already proved this underlying technology works by hitting speeds of nearly 99 Mbps. They're actively proving that they can turn space into a true high-speed cellular network.
AST SpaceMobile also has an incredibly aggressive launch cadence lined up. They launched BlueBird 6 from India in December 2025, followed quickly by BlueBird 7 on Blue Origin's New Glenn rocket in April 2026. Notice how they're strategically splitting their payloads across different rockets in different countries? This really highlights how these space companies have to carefully hedge their launch risks globally. Their target is to have 45 to 60 satellites in orbit by late 2026, and, crucially, they are well funded for this multi-launch campaign with a massive cash balance of approximately $3.5 billion.
Section 4. Rocket Lab. Launching the future.
So behind all this infrastructure is the logistics backbone. Rocket Lab is establishing itself as the premier small to medium launch leader, and the market is aggressively pricing in that dominance. Over a recent 3-month period, their stock surged an explosive 74%. When you compare that to the broader aerospace industry average, which just crawled up a measly 0.5% in that exact same time frame, it's crystal clear that investors are heavily weighting the vital importance of reliable launch logistics in this rapidly growing space economy.
The main catalyst for that massive surge? It's sheer operational momentum. Just in Q1 2026 alone, Rocket Lab secured 31 new launch contracts and locked in 5 dedicated launches for their highly anticipated larger medium-lift Neutron rocket. They now boast a massive total backlog of over 70 missions, and this includes strategic, high-profile defense wins like a brand-new $30 million contract for Anduril hypersonic launches. The demand for getting commercial and defense assets off the ground is absolutely surging.
Section 5. Risks, delays, and valuations. Let's look at the financial realities of space.
Now, time for a reality check. The headwinds facing orbital infrastructure are incredibly unforgiving. Systemic risks are literally everywhere. For launch providers like Rocket Lab, the highly demanding timeline for their new Neutron rocket brings significant execution risk. Plus, the wider industry is fighting severe supply chain bottlenecks, specifically for critical optical terminals. These are the components required for satellites to use lasers to talk to each other directly in space, forming a mesh network without having to bounce signals back down to Earth. Add to that a heavy reliance on U.S. government defense budgets and broadly negative returns on invested capital across the sector, and the sheer gritty difficulty of building in space becomes pretty obvious.
Valuation is the critical metric here. Space is a fiercely capital-intensive, high-cash burn environment. Despite all the amazing technological leaps we've discussed, investors are paying a huge premium for tomorrow's promises today. Rocket Lab, for example, has traded at a steep 68.28 times forward price-to-sales premium. That massive multiple means the market is pricing in absolute perfection in a domain where rockets regularly explode, timelines frequently slip, and supply chains break. We're looking at this data objectively just to underscore that the financial expectations baked into these valuations are incredibly high.
Which brings us to our final, provocative question for today. As hundreds of billions are poured into this AI-driven infrastructure supercycle, will these massive capital expenditures in space actually yield the orders of magnitude value that tech leaders have promised us? Or will the harsh physics of orbit, terrestrial supply chain bottlenecks, and the gritty financial realities eventually pull this booming market back down to Earth? It is undoubtedly the most fascinating infrastructure build-out of our lifetime, and you can bet we'll be watching every single step of it. Thanks so much for joining me on this explainer.